Good morning and welcome to the third and last day of our conference. And today we have a plenary talk that is going to be introduced by Professor Kalle Johansson. He is the president of the European Control Association. So Kalle, welcome and thank you.
Thank you, Thomas. Thank you very much. So it's my great pleasure to introduce the European Control Award plenary speaker, Peyman Esfahani. So Peyman is an associate professor at TU Delft in Netherlands. Before that, he held positions at EPFL, ETH, and MIT. He did his undergrad studies at Sharif University of Technology in Iran, and then he went to ETH and did a PhD there with supervised by John Ligorous. Peyman's research interest, as you will hear more about today, is in decision-making problems in uncertain dynamic environments with applications to control and security of large-scale and distributed systems. Despite his young age, he has already received quite some honors. He has received the Axelby Outstanding Paper Award from the IEEE Control System Society. So the best paper award basically of IEEE transactions of automatic control. He also received the Lanchester Prize for contribution to operations, research and management science from Informs. And he has an ERC starting grant. But of course, the most important award now on the CV of Peyman is for the 2022 European Control Award. So this award recognizes outstanding contribution by a young researcher under the age of 40 to systems and control, the systems and control area. But more about that after the talk. Now we are eager to listen to your plenary. Please, Peyman.
Thank you. Okay, good, it works. Thank you very much, Kalle, for a very kind introduction. I'm thrilled and honored to be here. It's a great pleasure. And I would like to wholeheartedly thank the award committee as well as the conference organizers to host this talk. So what I'm going to talk today is about a collection of works that I have been working on in the last few years. And first, I would like to thank and acknowledge my fantastic list of collaborators, PhD students, academic, as well as industrial partners that I have been working with them in the last few years. And without them, the things that I'm going to talk about today would not have been possible. I also would like to acknowledge the generous support of NW and ERC as well, of course. So I just have one slide as a motivation, just to give a context of what was the driving force behind the things that I have been doing in the last few years. So we all have seen unprecedented progress in the core area of automation, particularly thanks to the progress on two fronts, the sensor technology. Okay, it's too small, but anyway, I try to use it less. So sensor technology and computational power, and these two actually revolutionize many application domains, including energy system, transportation, manufacturing, robotics, and you name it. This discussion and this progress was not only about the industrial domain, also academic domain has had a significant impact by these developments, and in particular generates a discussion that how we can utilize tools and insight from these domains to somehow address the challenges emerging in this context, and in particular unleash the potential of these developments in different domains that we have. One of the domains that has received a particular attention is this health monitoring as a general topic. Within the topic of health monitoring, but I had the opportunity to work on three application domains. And in particular, security of power system. And by security, what I mean is both physical damages that can happen as well as cyber attacks. I also had the opportunity to work on water distribution network with a particular focus on leakage. And then also very recently, I got into a little bit top challenges of self-driving car. It's actually quite a timely topic, and people believe that it's going to be the future of our mobility. So there are some safety issues related to that. And today I'm going to touch some of the research questions related to this application. And with that, I don't think I need to say much. And I would like to, particularly on the water distribution, I want to cite an inspiring talk by Marius a couple of days ago, where we all convinced that actually water has a lot of challenges and relevant challenges for societal matters, and we could have an impact as a control community. So with this very short introduction, here is what I'm going to talk about today. So I'm going to talk about 3 topics. And telling the truth, when I was preparing the abstract, I just prepared the first 2. But somehow towards the end, I got ambitious and I add 1 more. But for a reason, and I'll comment on that. So the first topic, I'm going to talk about general problem of anomaly detection and in dynamics environments, and somehow touch these 3 application domains that I talked about. Then I'm going to move on to some generic topic of data-driven decision-making and type of research questions that pop up there. And then finally, some algorithmic approaches towards a well-known problem of dynamic programming. This subtitle that you see here is actually pretty much the main message that I want to communicate within each of these problem settings. So let's get started. So how do I see anomaly detection and how we can use actually tools from system theory as well as modern data analytics to address that one? That's a pretty standard problem in control literature, and it has been extensively studied. But I want to take a few minutes just to tell you how I see the problem and how I can actually connect to some of the tools that we have at our disposal. So think about this generic dynamical system in the presence of 3 different input categories. The D here represents natural disturbances that the system may encounter. F represents adversarial disturbance, fault or damages or cyber attack or anything on that sort. The U signal and Y signal, these green signals are available signals for us. Y is the input to the system, and Y are the measurements that we collect. So the problem of anomaly detection basically can be translated in the form of constructing a filter here, fed by these available measurements, such that the output of the filter, to which from now on I'm going to refer to it as a residual, tells us whether the system works normally or there are some intrusion or damages here as an exogenous input to the system. So to give you a little bit context, if I go back to this power distribution network, that would be somehow the representation of each of these elements. So this dynamical system is this huge power system networks. It's a nonlinear network. Then natural disturbances, the blue one, is basically all sorts of power imbalance in the system. The fault can represent the attacker's activity, and U signal all sort of information going from control room to the network. And then we have, of course, some measurements from the system like frequencies, voltages, and so on. And what we mean by residual is basically what is going to be monitored in the control room, and then someone there is going to assess whether something is going wrong or not. So hopefully this picture gives you a little bit feeling what I'm talking about. So with that, let me make it a little bit concrete what we expect from this residual to do. So think about this very simple scenario of these 2 unknown signals. So remember, we have 4 signals. 2 of them are unknown. One of them natural, the other adversarial, and the other 2 are known that is available to us and is going to be fed into the filter. So these 2 are just an example of unknown inputs. So the blue is the natural disturbances. And what you see here, you can think about it that the attacker is quiet up to here, and then at some point suddenly kicks in and changes something into the system. So what you ideally expect from the residual is the behavior like that. So you want the residual to be quiet, and no matter what the disturbance is, as soon as the attacker kicks in, it immediately reacts. So that's basically what you expect to see from the residual. And now I want to take this behavior and then try to somehow give a little bit geometric interpretation to that what we really see as a filter. So let me just very abstractly visualize the measurement spaces. So think about this very abstract three-dimensional space. These measurements, this is where these two measurements, the pair of y and u is gonna live. These 2 points are 2 samples of these measurements available to us. I deliberately make one of them blue and the other red, with the meaning that the blue one is gonna be the one that is collected through the normal operation of the system. So this is a point that is perceived as a healthy trajectory. And then the red one is the one that actually happened during the unhealthy trajectory or attack scenario. Now, throughout this first part of my talk, I'm going to restrict my attention to the linear filters, linear time invariant system. We can think about it even as a transfer function. And by doing so, what I'm saying is that the operator from the measurements to the residual is a linear operator. And we know that linear operator can be actually visualized as a hyperplane. So this filter from now on in my mind is just a hyperplane, and that's going to go through the healthy trajectory. It goes through the healthy trajectory because of what I expect here. So this should be 0, it should be insensitive, and that means that the healthy trajectory is going to be on this hyperplane, and then unhealthy should be outside. That's basically what I meant. Now, with that in a picture, we should remind ourselves that we don't have one healthy trajectory. As a matter of fact, we have many or potentially infinitely many of these trajectories. So basically, this hyperplane is expected to contain all the healthy trajectories. And what that means, that basically means that all the behavior, the healthy behavior of system should be represented by this filter, while the unhealthy one would be outside of that. That's actually a very classical concept in control literature, and it even dates back to 1950s and 60s by Jan Willems and Coleman. They call it actually behavior set. And just very recently, in the context of data-driven optimization, also data-driven control also got quite a bit of attention because of the very interesting properties that it has. So that's the picture in an ideal scenario that we could expect. Now, if we think about the nonlinear system, we immediately feel that expecting that this hyperplane goes through all the healthy trajectory is too much to ask for. So even this might not be possible. So the first step that you do naturally, you say, okay, what I'm going to do, I'm going to relax this 0 threshold and let the residual is going to react to other little bit. So that's going to be something like that. So the residual react, and then I introduce some threshold here, and I say, okay, as long as it's the behavior is surpassed by this threshold, I consider it as a normal operation. Otherwise, we say that something is going on with the system. When I'm doing something like that, now going back to this geometric interpretation, basically what I mean is that I'm no longer thinking about a hyperplane as a behavioral set, but rather a box. So this has something else. So this is basically what I'm talking about. So there's a box whose thickness could be actually represented by this threshold here, and that contains the healthy trajectories. And if I choose it appropriately, we could still separate from the nonlinear behavior aspect, for the unhealthy behavior aspect. So that's basically this is what I mean by problem. So what I'm looking for, in summary, I'm looking for a filter together with threshold, which visualizes as this thin box, in order to make sure that it contains all healthy behaviors, and then hopefully remain sensitive enough so that if unhealthy trajectory comes, it immediately leaves this space and I can access it as a anomalies in the system. That's basically what I want. Another thing that I want to ask you to pay attention to is what are the source of difficulties in this context, and I want to name 2 particular ones. The first one is the nonlinearity. That's actually what forced us to relax our notion to a box rather than a hyperplane. So that's one source. And the other thing that I want to emphasize on that is natural disturbances. Natural disturbances, you may have a bunch of them in the historical data set, and then you use it using any data-driven techniques, machine learning techniques. But what is really important is that what happens if now I pick this and go to the real-time operation, and then I happen to have another disturbance that I hadn't seen it in the past. Does that threshold respect it? Does the filter recognize it or not? These are the questions that one has to answer. And if you think about it, basically what I'm saying is that how likely I'm going to have a healthy trajectory outside this box. And speaking of how likely, you can actually connect it to a terminology in fault detection or anomaly detection, knowing as false alarm. So basically, you would like to make sure that you design these things such that the probability of violation the threshold, or equivalently, the number of healthy trajectory outside this box is going to be limited. So that's the problem that I'm going to address today and try to solve it. And these are the boxes that I will get back to that. Okay. So now let me give a little bit more context, a little bit how the mathematical formulation of this problem looks like. So the model is going to be this model that we have. It's a classical nonlinear differential equation or nonlinear difference equation that we have. This plus here could represent either differentiation operator or time difference, depending on the time setting that you have. For the purpose of this talk, doesn't make difference if you go with continuous time or discrete time. You see that there are some linear part, but there are nonlinear part as well. This is generic nonlinear terms. Now, what I'm going to do, I'm going to massage this to make it a little bit convenient for the later analysis. So what I'm going to do, I group these signals together in 3 ones. This 3 is actually similar to the 3 ones that I mentioned. So the blue ones, which are the internal state and natural disturbances together as some unknown signal, but the one that I don't really care. The green one is the one that I can measure it. It's going to be the input and output of the system. And then finally, the false signals, the red signal. Now, what I'm going to do is a very simple algebraic operation. I just introduce these matrices, and I turn this all the way down to this so-called differential or difference algebraic equation. So basically, it's just pure algebra going down. What perhaps is interesting to pay attention that this plus is no longer there, but what I have is P parameter, and P represents a differentiation operator or difference operator. So the main reason that I do this is that basically now I managed to split the role of each of these important parameters. So now then a blue signal is going to appear here with linear term. Here the green one, here is the false one, and all the nonlinearities is going to be encoded to this EQ. So I have 4 terms that I need to work with that. So hopefully in this slide, I managed to convince you that I'm going to stick to this formulation, but hopefully you got the impression that this is general enough to actually capture what we have up there. Okay, so now this is perhaps the most technical part of the slide for today. I just want to give you an impression of how we design this filter through an optimization scheme. This is what I started with. These are 4 terms. The first part is just to remind ourselves, this is the nonlinear term. This is what makes our life a little bit miserable. And this is also the group of signals that we have. And that's how these inputs are going to connect to these outputs. Now, the first step to design the filter is actually designing an X of P. What is this X of P? This is, I deliberately put it in green because this is the design parameter that I have. You will see in a minute how it is related to the filter. But all you need to know that HP was a matrix where the elements are polynomials in P. And XP is going to be a row vector whose elements is also polynomial in P. The coefficient that is on my side is going to be the coefficient of X of P. All I ask for that this multiplication is equal to 0. Let's start from there and then see what happens. So now I multiply this equation by X of P from left-hand side. By construction, the second term disappears. And then by reordering that, I end up with this simple equation. That's basically keeping the green one on one side and bring the other 2 to the other side. That's just a simple thing. But now something's interesting happening here. One side of this equation is all green. That's exactly what I can measure it. And now I know how it looks like as a combination of the blue and the red one. That's basically what happens. So this is exactly the filter that I'm going to pick up. So the filter here is the XPLP. It's going to fed by the measurement Z that I have, and this is the residual. And on the other hand, based on the model that I have, I know it's the combination of these 2 terms. And you know what are these 2 terms? Let me go back to the very beginning figure that I show you. You remember that this is a type of behavior that you expect. The behavior of the residual in the first phase is due to the first term here. And the behavior sensitivity on the second part is due to the second part. So that's exactly how I use the model to somehow get hands over the behavior of the residual in different phases that I expect to behave as I explained. Now, that's pretty much the end of the conceptual part. Now we need to translate each of these terms. So just to remind ourselves, the first term, I want to have it as minimum as possible. The second term, I want to make sure that it's going to remain sensitive up to a certain extent. And then I have this one as well. So I can actually put these three together and start transforming into a mathematical object, in particular mathematical programming, so that I have an optimization program at the end of the day. The first one is an easy one. Of course, I'm not going to show some of the details, but the details are very much algebraic. But the point is that this equation is just basically a linear equation on the coefficient. So perhaps you are not surprised that I say that this is just a linear constraint on the coefficient that I have. X here, I abuse a little bit of notation. So this X is actually the collection of all the coefficients that I have in X of P. Then between these two, let me start from the second one. Now, something that is also quite perhaps a little bit unexpected, that despite the nonlinearity of the system, if you look how it disappears, you see that you remember XP and FP is a linear operation. It's a linear transfer function, if you wish. Okay, so I now have actually a linear operation from the fault here all the way to the R, despite the nonlinearity. So all I need to care about is to control this mapping as a linear transfer function to make sure that it's sensitive enough. And sensitive enough, in this work, we basically pick up a very classical concept of H infinite norm of the transfer function, and I put it here. How the H infinite norm of such transfer function looks like, that's also a little bit algebraic technique, but you end up with an infinite norm of a matrix multiplied by the coefficient that I have. So that's also somehow that I have control over. But it remains the most problematic one. This object is the most problematic one. And it's problematic because this is exactly the guy that takes the care of the nonlinearity, as well as where these unknown disturbances are. So what we managed to do is we look at this as a signal and then look at the energy of this signal. And energy in a proper sense is that L2 energy of this signal. And what happens is that this energy can be conveniently written as a quadratic function of the coefficient that we have. Being quadratic is also not really surprising, because if you look at how XP appears here, it's linearly. So if you look at the energy of that, you are not surprised by the quadratic part. But what is very interesting is the quadratic semi-definite matrix here, this QD. This is perhaps the most important object of this work. So what are these objects? First of all, this is the object that takes care of nonlinearity of the system. But this is also the same object that takes care of the disturbance information, what type of the disturbance pattern I encounter. And finally, which you can see it by construction, is that if the system happens to be linear, this complicated object by construction is zero. So you can actually say that this is the object that takes care of pure nonlinearity of the system. There is no linearity in there. Now, this object has two properties. Let me start from the bad news. The bad news is that if you want to analyze this, by the way, you remember the source of difficulties. All of those that I mentioned earlier is encoded into this positive semi-definite matrix. So the first thing is that if you want to analyze this as a map from a particular natural disturbance to a positive semi-definite matrix, this problem is as hard as the original problem. So this is exactly where all the complication is there. But the interesting point is that if I give you a particular pattern, you can actually compute it point-wise. How to do that is basically simulate the system. If it is an ODE, you can actually simulate the ODE, compute this QD for the particular pattern of the natural disturbances. If it is discrete time, you just run an algorithm, 10 steps or whatever steps that you are interested in, and then you get this positive semi-definite matrix. Being able to compute this actually gives immediately an idea to use our learning tools. And in particular, that could be where the data analytics kicks in. And then you use the data and simulator to compute this QDI, at least for finitely many disturbances that you have, the disturbance patterns that you have. So with that, basically you can put all these things together. This is an optimization problem. It's called a scenario program, in the sense that you need scenarios of disturbances in order to construct the first, to take care of the first term. And the other two terms are handled nicely as a mathematical programming object. So this optimization problem is effectively a convex optimization. It's actually effectively a quadratic program, a convex quadratic program. And that actually quite handy to solve it in real time. This optimization program, like all optimization program, has two outputs. And these outputs are optimized and optimal value. And guess what they are? They are exactly what we were looking for. So the coefficients is the parameters of that, and the optimal value is the threshold that we are interested in. And that's how we design our filter. So in summary, that's what I told you so far. So I try to use models and data to construct a convex optimization. Just to remind us that these F and H are coming from the linear part of the dynamics. And QD also comes from the nonlinear of dynamics, but evaluated at data points. So that's basically how we build up a convex optimization. And then we can solve it and put it in place. But there are a number of questions that I need to answer. And that is, how many samples do I have? Which guarantees I can expect for, how I can implement it in real time, and so on and so forth. So these are the questions that I'm going to answer later in the second part of my talk. But before that, I want to go to a little bit those three applications and show you how this looks like in practice. Let me just take a. Okay, good. So that's basically the optimization that we solve. Let me go back to this. This was the first project that actually I started towards the end of my PhD. So this was a power system application. How this power network looks like, at least on paper, let's say a decent complex model that we have would be something like that. So you can model it within a certain setting, a nonlinear ordinary differential equation with about 59, 60 states. So as a nonlinear dynamical system, we know that 60 dimension is quite high, at least from a computational point of view for designing things that we are interested in. It's a nonlinear system. The number of disturbances that we have is going to be 19 disturbances that has impact on the generators of the network. And then we have about 38 measurements, and then some attack in certain loop, so-called AGC, automatic generation control loop. So how it looks like for a simulation. So what you see here on the left-hand side is a collection of the samples of natural disturbances. And then you see that the attacker is quiet up to here, and then suddenly change something in this particular signal for some values. And that's the reality. Reality in the setup that I have. Of course, this guy here has no idea about that, but this guy is going to see as a measurement is these two measurements. So these measurements are what we collected here as, for instance, frequencies and voltage angles. If you look at what is happening around 30, where the attacker kicks in, you barely see any difference, even for an expert eye. And the main reason, actually, from a physical point of view, is that these quantities, all of them have the same unit. All of them are power. So you see that the attacker's activity is actually 1/4 or 1/5 of some natural disturbances. So it's not really surprising that you don't see anything. But now when you design the filter the way that I said it, and you look at how it looks like in the residual, that's exactly what is happening. Of course, there are some reaction here during the healthy operation, but that's exactly the price to pay to gain scalability and go to a higher dimension like 60 dimension. So this was just to give you a little bit impression how the results looks like, at least in the simulation. So after that, this was actually a collaboration with ABB, but later when I moved to Netherlands, I had a similar collaboration with Tenet, a transmission system operator there. And then we look at also some other aspects of this problem, particularly, for instance, what happens if attacker has access to several points and try to manipulate them and still deceive the filter. You can actually introduce some sort of game between the attacker. You might be also interested to put a more serious application in which you add hardware to the discussion. And these are the cases that you actually don't even have the nonlinear dynamics to start with. It's just some high fidelity simulator. So how you can do that? So there are some small direction that we also had here. If you are interested, you can look at those works. The other application that I wanted to comment on that, but thanks to Mario, so make it very short, is the water distribution network. Prior to this project, actually, I didn't know that leakage is so common phenomenon. So in this application, the question is not whether we have leakage or not. That's for fact is. The question is where it's happening. So localizing leakage is a very important thing. And from both practical and research point of view, the difficulty of this kind of applications is that the signal to noise ratio is quite low. So you need to engage with the system, to excite the system to do what you want it to do. Passively and just measuring, it's not going to work. That means that this signal, this U, is also part of the design. It's not only about the filter. That's what is known as active detection. The final application that I want to just very recently start, this is self-driving car. You can see that this is also can fit into this framework. The dynamics is the vehicle dynamics. And there are natural disturbances like road curvature. This is a collaboration with Siemens and TNO. There I got actually to know that there are some relevant challenges there. For instance, these two particular faults, like changing a little bit of tire pressure or friction of tire in principle, and then some offset in the steering angle. So it can be detected in real time or not. And that's how it looks like. These two faults actually influence the system in a totally similar way, like natural disturbances, that basically from a driver's seat, you see that the drivers start drifting away from the middle of the road. But from dynamic point of view, the question is, can you separate one from another? Another thing that was interesting is that they are not only interested to tell them that you have an offset, they want to know what is the offset. So basically in control language, what they want that this are not only react, but after a while track what the fault is actually at the source. So it's a pretty much tracking problem that we have. So these are two things that I work in this application. This project actually we had the opportunity to also implement it experimentally on the car of provided by TNO. This is what you see as a trunk. This is exactly what all this computation happened. This red one is pretty much the brain of the car, and that's where these optimization problem that I told you is being solved here. And what you see here on the right-hand side is the real experiments. These are the measurement. Of course, we're smoothing out, but this is the real measurement. There are two faults here. Both these faults actually we injected to the system, and then we try to detect it, and then it works decently. They are definitely not as beautiful as what you saw in the previous one in simulator, but they do the job. Okay, so that's pretty much the first part of my talk. So it's about anomaly detection, how we can use both model and data. In the second part of my talk, I want to switch the topic. So if you missed a little bit something in the previous part, you don't need to worry about. That's basically the topic about how we can now in these data-driven techniques and data-driven decision-making, we provide certain formal guarantees. And the main focus that I would like to have here is to, first of all, give you a little bit impression of what type of research questions are out there, how people in different communities, actually it's a subject that people from different communities looked into it. They give some different names to the same thing. And my point is not to give you very exact theorem and proof, but rather what type of research questions are out there. So let me start this. And then I will show you how the convexity will show up in several levels. So any decision-making problems involves three fundamental objects. The first one is the loss function. That's loss function is basically what you care about. And then you have decision and uncertainty. In pretty much all applications, you rarely have access to the distribution that describes the behavior of uncertainties. All you have is data, and you make a decision based off the data. And if you want to think about it, how you formalize this conversation, you can think about it as a map here that you get the data. You can think about the data as a past. You turn it into the decision, which you can think about it of the present. And speaking of guarantees and performance, what we really care about is not how the performance of the decision on the past data, but rather how it evaluates on the future data that we didn't see. That's what basically is about. The conversation of performance starts from here. And just a flashback to the anomaly detection problem, that's basically the role of them. You remember that I have natural disturbances. The decision that I was making is filter and the threshold. The question, interesting question, is not whether this threshold is going to respect these natural disturbances, that by construction trivially holds, but the question, what if a new one pops up and whether this threshold is going to respect that one. So from a mathematical point of view, now there is a difference between the loss in the future and the loss in the past that you have seen. So this picture is actually pretty much at the core of all these data-driven data analytics or machine learning. People in machine learning community actually give some, in my opinion, natural names to the objects that you are seeing here. You might have all heard about training. The first arrow here, they call it training, makes sense. They call also the second one test. And the difference between the future loss and the past loss, they call it generalization error. So the gap that you see here between these errors and that one is what they call it generalization error. So what I started looking again, I'm working with operational research people, I actually got to know that they are a little bit more creative in names. So what they call in the training phase, they call it prescriptive analytics. What they call about tests, they call it predictive analytics. But perhaps the best part is what they call generalization error. They call it post-decision disappointment. So that's what they call it. Sounds fancy. Yeah, credit to their creativity. Okay, so that's the starting point of the statistical side of data-driven. So they want to understand how this gap looks like. And now here, from a technical point of view, things become relatively complicated. And complicated in the following sense. We are talking about an object, future loss, that has two sources of uncertainties. And this is quite critical. So the decision is one sort of uncertainty depending on the data set that you get in the past, but also the future loss. So these are two sources of uncertainty with different meaning, and that actually is starting point of the complication when you want to formalize this gap. So I want to very briefly comment how people look at this loss function with two sources of uncertainty. So think about future loss. Remember, loss in the future is not one variable, it's actually a distribution. So this is the distribution of the loss in the future. There are different ways to turn a distribution into the real value to say whether you are good or not. This is what from a technical point of view, they call it risk measure. So there are different risk measures. Arguably, the most popular one is expected loss in the future. This is basically at the heart of statistical learning in machine learning and in statistics. But there are other ways to measure future risk. So worst case risk is another one. So you look at the worst loss that you're going to see in the future. There is a little bit relaxed version of that. People in operational research call it value at risk. Basically, what value at risk means is that you allow yourself to ignore epsilon percentage of future loss, epsilon in terms of likelihood. And then you say, what happened after I cut the tail of epsilon? So that's the value that I'm talking about. In other communities like control, people refer to this quantity as chance constraint. So this just, again, another time, total, same object, different names. So value at risk and chance constraint is exactly the same thing. And if I want to put it in context of anomaly detection, in the first part, this is basically probability of false alarm. So that's what we are interested in. So if you manage to make a control number 3, basically you control the probability of false alarm. That's the interpretation. Now this is how we look at the second arrow. Now switching to the first arrow, I want to put all the techniques that I have seen at least in the literature into one context. This is also has a little bit mouthful name. It's a distribution robust optimization. This is the way that we turn our data into the decision. But what it basically means is that I minimize the worst case expected loss, where the expectation runs over a family of distribution. This is what the people refer to it as an ambiguity set. The choice of ambiguity set is a central object for the distribution robust optimization. You have many, many possibilities. And which one is appropriate depends which one of these guys you care about. So it's not a uniform answer for that. So for this talk, I want to just point out two things. One, perhaps, before getting there, how the guarantee looks like, I should point it out. This JN is something that, remember, you can compute based on the past data. The type of theoretical bound that you care about future loss goes through this J hat N. Sometimes people refer to it as a certificate, and that's also a reasonable name for that. So we want to know where this certificate actually is going to live on this axis. But then here, if you remember, the first part of the complication kicks in. So about the loss function, that's not a single value. This j hat n is also in principle a random variable inheriting the randomness from the data set. So if the data set changes that you're given, this object also changes. So when I'm talking about certificate, I'm talking about the bounded distribution. But it is green because it just carries over the stochasticity here all the way here. So the question is how the green distribution looks like in comparison with the blue one. That's basically the context of data-driven decision-making problems from a performance point of view. So that being said, I just briefly comment on two common ambiguity sets that I came across. The first one is related to the expected loss. This is the one that's very popular, and one of the possibilities is to define ambiguity set as a ball in the space of distribution for which the center is usually a nominal distribution. That's exactly where you use your data. So you use your data to basically introduce a candidate, and then you put a ball around it to make sure that it's robust with respect to whatever that you are interested in. And that's a possibility to do. In these kind of things, one of the key question that you have to answer that this first arrow is going to be computationally tractable. Because if you look at it, in principle, this is not only a min-max problem, but the max part runs over an infinite dimensional spaces. So this makes this first arrow potentially intractable. So that's also at the heart of the question that you need to answer. The other ambiguity set that I want to talk about is more about the other two risk measures. And I think this is where we could give credit to control community, because at least to the best of knowledge, people in the control community address some of the questions here. In particular, this scenario program that I mentioned earlier can be viewed as an ambiguity set where you have Dirac distribution on each data point. And what that means is just a fancy way of writing minimization and worst case loss. Okay, that's what is pioneered by a few researchers, Marco Campi, Giuseppe Calafiore, and also Simone Garatti. They develop a lot of interesting results in that direction. And they actually show how J hat n is going to be connected to the number 3, the value at risk. So this distribution, actually, interestingly, is going to be very fast shifted to the right-hand side of the number 3. So here I can tell you two results in the literature. The good news is the result that I just said. So this J hat n is going to go above number 3, very fast and totally independent of the distribution. It's going to be heavy tail, it's going to be infinite dimension, whatever. If you manage to solve this problem, the J hat n that you get has this kind of behavior. Of course, you have to write it mathematically how this looks like, but that's basically the message. The second news is the other side. The other side is more of a bad news, that actually when n increases, of course, under some regularity condition, it takes ages for this distribution to converge to number 2. And this is something inherent. It's not that you can actually make this exponentially better or something. You really need to put a lot of effort to reach to number 2. In a way, I'm saying that in our many examples that the gap between 3 and 2 could be huge. That's basically what I'm saying. So these are the second kind of questions. So you remember I mentioned about the first part as a computational part, the second part, a statistical part. There's a third part that recently also got quite a bit of attention, and that I would like to put it as a real-time implementation. And what does real-time implementation is another research question that got quite a bit of attention, and that is that we do not want, if I give you a new data, you do not want to put it here and solve the whole program from the scratch. Ideally, you want to have an algorithm that take the current decision and new data and turn it to the new decision variable. This is quite important. And in this context, like online optimization and regret bounds are the common topics that show up here. Actually, what I found it interesting is that nowadays the credit is more on the machine learning community. If you go back to 50 years ago, actually people in control community developed Kalman filter by the fact that it managed to actually make it exactly equal. So you need some regularity condition on the function L in order to make sure that you solve it. If this problem happened to be quadratic, this approximation can be exact. And then you can actually have recursive formula, and Kalman filter is a result coming out of this actually property. So what I want you to have as a takeaway message of everything that I said is basically where the convexity shows up. And what is very interesting to my knowledge is that actually convexity turns out to be useful for all these three questions. Obviously, convexity is important to be able to solve this problem efficiently. That's not that much surprising. We all know that the convex optimization are nice from a computational aspect. What is perhaps more surprising is that, and Campi and Calafiore and Simone showed, that actually this kind of convexity can help for locating the J-hat-n on the right-hand side, the statistical aspect. That sounds quite surprising, at least to me. And then finally, to be able to solve this in a recursive version, there are very recent developments quite promising how to do this through an algorithm. And that also where the convexity helps. So this is basically how I see the role of convexity in data-driven decision-making on three different levels. So that's the first part, the second part. And now this brings me to the last part. This is a very short part and a little bit different than the others. But the main reason that I included it is the interplay between some computational aspect and system theory. How system theory can actually help us to gain some computational benefit. So what is the context about? It's about dynamic programming. Dynamic programming is actually the main workhorse at the heart of optimal control and reinforcement learning. How does it look like? It's basically, this is how it looks like. The U is the control action, X is the state of the system, and F is dynamics. But if you haven't met this before, you don't need to worry about what it's probably important to know that dynamic programming can be viewed as an operation from functions to the functional spaces. So you can think about it as an operator that you give a function and then you pass it through this optimization, partial optimization, and you get another function. The direct computation of this operation has a complexity of n multiplied by m, where n is the number of states and m is the number of actions that you have. This basically means for any state, I compute all possible actions to make sure what is the best value. That's basically it. The question that we are trying to answer here is that, can we do better than that? Can we reduce the complexity, the direct complexity of n multiplied by n? To answer this question, I want to go back to some very classical result of linear system theory, and then see how we can get some inspiration there. So what is linear system? We can see the linear system as a way of operation between signals. So this linear system takes this signal and turn it into another signal. How linear system looks like? We all know that it can be described through a convolution operator. This convolution operator is a complex operator because if you need, for instance, compute the value of the output at a particular T0, you need the information of the entire history, potentially entire history of the input variable. So a single value can depend on the entire point. That's what I mean by complication. What was revolutionary in system theory is when we start looking at this operation in the dual domain, in the frequency domain. So when we go to the frequency domain, this input-output relation becomes quite interestingly simple. So that can be translated into simple algebraic multiplication, which we all know about as a transfer function. And it's not only simple from operational point of view, but also from information point of view. If you need a point now in the particular frequency, all you need from the input is a particular point in the input as well. So you don't need to know the entire frequency content of the input to know about the output. That being said, and by the way, this simple observation is actually the backbone of many of fundamental results that we have in system theory and control. But that being said, if now I compute this guy and I want to transfer it back to the time domain and know how it looks like in the time domain, I have to pass it through the Fourier transform again. And that could be potentially complicated. And then here is a signal processing community offers a very elegant algorithm known as fast Fourier transform. This is a pure algorithmic technique that can break down the complexity of n squared to effectively log n. This is first credited to Cooley and Tukey in 1965, but it actually turned out that even before that, these people had known about it. It was during the Cold War, and where US was spying on the nuclear facilities of Soviet Union. And they knew it, they didn't publish it, but later, about 10 years later, they published it. This algorithm turned out to be actually quite influential in many domains, and recently it was selected one of the top 10 algorithms in the 20th century. So it was a quite important algorithm in a scientific domain. Now you may wonder why I'm showing you this, how this connected to the dynamic programming in the first place. Now let me go back to the dynamic programming that I started with. So the very first question is, can I have something like that here as well? Is there any operator similar to Fourier transform for the functions? And it turns out that there is an interesting object, and that is conjugate operator. So convex conjugate operator, I don't write the mathematical description, but it's not important to convey the message that I have, is that this object, this actually behaves sometimes very interestingly similar to the Fourier transform. What is interesting from a similarity point of view, that actually both of these operators are the so-called unitary operator on unappropriated spaces. So we know that Fourier transform on L2 spaces, if you apply it twice, you get the same function again. That's also happening with convex conjugate operator for convex functions. So if you apply convex conjugate operator twice, you get the same function. But despite this interesting similarity, they are fundamentally also different. The Fourier transform is a linear operator, but convex conjugate operator is a nonlinear operator. What I personally found it extremely astonishing is that one work not actually quite a long time ago, they realized that if they change the underlying algebra, if you change the definition of summation and multiplication, then actually Fourier transform and conjugate operator coincide one another. So the conjugate operator in a new algebra known as max plus algebra is actually exactly like Fourier transform. And this actually helps us to complete this picture in the sense that you can actually go down under certain conditions, which is not trivial, at least for us, is you can write down the dynamic programming operation in the dual domain. And then interestingly, under those conditions, this operation also looks like effectively like a summation. And summation in the sense that if you now need information of the value function of a particular node, all you need to know about the function in the first place is just one particular node as well. It might be also interesting to point out that this summation is actually in the new algebra is multiplication. So this really looks like a transfer function in a way. What is also interesting and should be credited to this work by Correas is that they use this connection and they translate the fast Fourier transform into fast convex conjugate operator. So now we also have an algorithm to compute this fast as well. I mean, this line fast. So we use this as an oracle for ourselves. And then I go down, and what it turns out that the complexity of the down path is going to be n plus n. So that somehow the benefit that we get from the down part. And if you think about that, for instance, you have 1,000 states, 1,000 action. The complexity of the top part is 1 million, whereas the bottom part is about 2,000. That's going to be a huge benefit from that. When I was working on that a year ago, I was quite excited because I thought that this is not actually what we are seeing here as a reduction is not the full potential of this. We knew that fast Fourier transform actually has quantum computing algorithm for that. So people in quantum computing community develop a fast Fourier transform algorithm. So we thought that if someone can write down these objects also using quantum computing and the algorithm there, we could also break down this complexity more than that. That we were quite excited about. And this vision that I'm picturing for you was not only hypothetical. Actually, about a few months later, 6 months later, people in IBM Zurich actually introduce a quantum algorithm to implement this part. So they pick up our algorithm, they turn this into a quantum object, and then they can break down also to log n plus m. I have to say that we were quite excited when we see this because we thought that for the first time we could break the curse of dimensionality, the infamous curse of dimensional dynamic programming. But I have to say that our excitement didn't last long So what happened is that after that, there is another community. This is all quantum computing community. Some people from University of Waterloo came up with some counter argument, and they argue that this is there's a flaw, there is not possible to achieve it, and the best that you could do is the square root of n if you break down this using quantum computing. I'm still happy to see a square root of n, but yeah, that's not as exciting as before. But anyway, this is totally outside of territory that I can give any educated comment. But with that, I would like to thank you again for listening. And here is the base, the references that this talk was about. And thank you.